This video deals with surface tension. Molecules in a fluid feel a mutual attraction, and generally a fluid system will act to minimize the surface areas because that minimizes the energy that they have to spend to keep close together. So if we have something like this water here, you have the water molecules in the water that are surrounded by other waters, and then on the surface some molecules are attracted to the water that's here, but there is no other water on the surface of the water. In general, what molecules do is then they want to minimize the surface area, and minimizing the surface area means that spheres are formed, because that is the lowest surface area that they can achieve. So small fluid bodies will tend to evolve into spheres, just like it happens whenever you have a faucet dripping. You will see that they will be as spheres. If we look at U, and we call U the total cohesive energy per molecule, and sigma is the surface tension, what we see is that in the surface, on a flat surface like we saw before, we had a flat surface and the total cohesive energy is U, and the molecules that are on the surface then will lose half of that energy. If we say that R is the characteristic molecular dimension, or radius in this case, then the surface tension is approximately equal to the total cohesive energy divided by 2R squared. That means that the surface tension will be proportional to the total cohesive energy per molecule and inversely proportional to the characteristic molecular dimension, or the radius. This surface tension is measured in dynes per centimeters, because that's the distance that a molecule per distance that will have that force. For oils you have about 20 dynes per centimeters. For water is about 70 dynes per centimeter, so water has more cohesive energy. And for mercury, which is a liquid metal, it's even greater. And you can see this if you ever have seen mercury, you display it and they will try to stay together. So it's a lot of attraction. 1 Newton is 10 to the 5 dynes. So whenever we talk about interfacial tension, is a property of a fluid-fluid interface that acts to resist the creation of a new interface. So whenever there's no interfacial tension, the water is miscible, such as in this case where you have salt water and fresh water. So that's miscible. It tends to immerse together, doesn't want to keep its own face. Moisture is held in the fine pores of soil. So whenever we talk later on about groundwater, the groundwater is going to be found in the pores in the ground, in the subsurface. That water can be drained easily or not so easily. The larger the pores, the more easily that is drained, and the smaller pores drain only at high capillary pressure, meaning that in small pores it's hard to remove that water. That will retain in the water. So there's a relationship between that capillary rays, and as you can see here, you have a small radius versus a large radius, and we have here the height at which that is the capillary rise is a lot larger whenever you have a smaller radius diameter. So the same thing applies for pores, small pores or large pores. So the capillary rise is the relation between the holding capacity of the soil and the tension. So this is the equation that describes how much will be that height, And the capillary tension will make, in the case of water, you have this angle theta, because the water wants to minimize the surface area, so it's going to be, especially on glass, it will be form that meniscus there. So H is the capillary rise, R is the capillary radius. In this case, you have here this radius, and gamma is the surface tension of the water-air interface. So you can get this capillary rise under different conditions of density, and G is the acceleration of gravity, and for different radius. I want to talk briefly about the difference between field capacity and wilting point. The wilting point represents a soil moisture tension where plants can no longer take moisture from the soil, whereas the field capacity is the water remaining after short drainage of the soil. So you can have a soil that has a high field capacity, but that doesn't mean that all of the water in that soil will be available to plants. That water has to be available to plants, because plants don't have a way of increasing the suction out of the soil only to a certain point, and that is the soil moisture tension, where plants can no longer take moisture from soil. So this is a figure that expresses that difference between the field capacity and the wilting point. So whatever soil you have, if this is the wilting point for the plant, then you have a field capacity. That means that all this here is going to be the water available to the plant, because here the field capacity is larger than the wilting point. So that if you have the field capacity of the soil this high, that means that all of this water will be available, and any water that's here is not available to the plant. This water is available to the plant, and anything above the field capacity as well, because then that's excess water above the field capacity. So you have not drained the soil in this area. You still have larger than the field capacity, meaning you have some gravity water still there. So you want to look for soils that will have more available water in times of drought. If you have a soil here like sand, you don't have a lot of available water for the plant, and you can see that because the sand drains easily, and so you will not have a lot of water available, only 10% at the field capacity. But if you have clay, that has a 35% field capacity, but then you don't have as much water available between irrigation. This here shows the figure where it shows the available water capacity. So you want to choose a soil that gives you the largest available water capacity. If you have sand, it'll drain, it'll evaporate. If you have clay, also a lot of that field capacity is reduced, because you can retain a lot of water, but then the plants do not have a lot of that water available.